All right, so today we're taking a deep dive into something pretty remarkable. It's been called the most beautiful theory in physics, no less.
Mhm.
Quantum field theory, or QFT for short.
Yeah.
And it's really the bedrock of the standard model of particle physics, which, as you know, is our best description so far of the fundamental particles and forces that make up the universe.
That's right.
So today we're going to try and unpack this for everyone
Sounds good.
to really get to grips with what QFT is all about and why it matters.
Absolutely. And, to fully appreciate QFT, it helps to take a little trip back in time. For centuries, the workings of the universe, they must have just seemed utterly random, even miraculous to people trying to make sense of it all.
Yeah, definitely. And as your sources point out, things really started to shift with thinkers like Galileo and Newton.
Right.
The universe suddenly started to look more like a predictable machine, like this giant clockwork mechanism.
Upward universe, yeah.
Yeah, and classical mechanics with its elegant equations,
Uh-huh.
it gave us this incredible ability to model and understand things like, a planet orbiting a star with remarkable precision.
Yeah, it was a huge leap forward. It really showed the power of deterministic laws in explaining the natural world.
Exactly. And so for you, that was a real foundational moment in physics, I think.
It really was.
But then as we move into the early 20th century, our understanding takes another dramatic turn, and this is highlighted in some of the sources you've been reading.
Yeah.
Relativity and quantum mechanics come along, spearheaded by these giants like Einstein and Planck and Bohr and Schrödinger, and they reveal the universe that was far more bizarre than anyone had imagined.
Totally.
Time wasn't absolute anymore, it was relative, and the location of a particle, well, as you've learned, it wasn't a certainty.
Yeah, it became more about probabilities.
Exactly, and this is where things get really interesting, because just when we thought we were getting a handle on quantum mechanics,
Right.
another paradigm shift happens, and it might not be as widely known, but it's arguably just as profound. This is the birth of quantum field theory.
That's right.
It basically took quantum mechanics and made it even more powerful, more complete.
Yeah, filled in a lot of the gaps.
And so our mission today is to really try and understand what QFT actually is, why physicists realized quantum mechanics just wasn't enough, and how it fundamentally changes the way we view reality.
Yeah, that's a great goal.
So maybe a good starting point would be to look at where the older framework, standard quantum mechanics, where it started to show its cracks.
Sure.
We talked about the success of classical mechanics with planetary orbits.
Yeah.
Now let's consider a similar system, but at a much smaller scale, an electron orbiting the proton in a hydrogen atom.
Okay.
So we've got a positively charged proton with a negatively charged electron attracted to it. It almost sounds like a miniature solar system, right? So if we follow the logic of classical mechanics, it should behave in this predictable, stable orbit, right?
In theory, yes. But that's where classical mechanics runs into a really big problem, and this is actually detailed in some of the foundational physics principles that you've been reading about.
Okay.
According to Maxwell's laws of electromagnetism, any charged particle that's accelerating emits electromagnetic radiation, and an electron that's constantly changing direction as it orbits a proton.
Right.
Well, that is, by definition, acceleration.
Okay, so let me see if I'm following you correctly here. This orbiting electron, it would continuously lose energy.
Yes.
In the form of light, so in the form of photons.
Precisely. And if it keeps radiating energy, what inevitably happens to its orbit?
Well, it would have to spiral inwards, right?
Yeah.
Closer and closer to the nucleus until eventually it just crashes right into it.
Exactly.
That doesn't sound very stable for atoms.
No, it doesn't. And, that simply doesn't happen in reality. Atoms are remarkably stable.
Yeah.
Electrons don't just plummet into the proton. So this fundamental contradiction was a clear sign to physicists that classical mechanics, despite all its success on larger scales, it just wasn't adequate for describing the atomic realm. A new approach was needed.
And that new approach that you've been reading about was quantum mechanics.
Right.
And a really pivotal early idea was Niels Bohr's proposal that electrons could only occupy specific quantized orbits around the nucleus.
Yeah.
Each corresponding to a discrete energy level.
Right. A minimum energy quantum, as he called it.
Right. And the electron couldn't exist between these allowed energy states. And importantly, it couldn't fall below that lowest energy level.
That was crucial for explaining the stability of atoms.
Absolutely. It was a revolutionary step. And it completely changed how we picture these tiny constituents of matter, I think.
Yeah.
Because in Newtonian physics, we think of particles as these tiny, solid objects.
Yeah, little billiard balls.
Right, with well-defined properties, a precise mass, a precise momentum and location at any given moment. But quantum mechanics, as your sources highlight, really upended that neat picture.
It did.
Suddenly we're dealing with wave functions.
Right.
These mathematical descriptions that are governed by the Schrödinger equation.
Yeah, a whole new way of looking at things.
Absolutely. It's a completely different way of thinking about reality at that scale.
Definitely.
So the location of a particle, it's not known for sure until we actually make a measurement.
Right.
Before that act of observation, all we have is a probability.
Exactly.
The wave function provides the likelihood of finding the particle at any specific point in space. So you can think of it as a kind of fuzzy cloud surrounding the nucleus.
Yeah, that's a good analogy.
Where the density of the cloud represents the probability of the electron being there.
That's right. The denser the cloud, the higher the chance of finding the electron at that point.
Right. So instead of those nice, neat, well-defined orbits, we have these probabilistic distributions.
Yeah, it's much more uncertain, or perhaps more accurately, a statistical description.
Right. And as we touched on earlier, even this groundbreaking quantum mechanical view, it had its limitations.
It did.
And you've probably come across this in your reading. Where did standard quantum mechanics start to fall short?
Okay, well, one of the main limitations was that quantum mechanics in its initial formulation wasn't relativistic.
Okay.
It wasn't compatible with Einstein's theory of special relativity.
Right.
And this incompatibility meant that it would give you incorrect predictions when you were dealing with objects moving at speeds approaching the speed of light.
And the implications of that are pretty massive, right?
They are.
Because the universe has a speed limit, the speed of light.
Yeah.
And quantum mechanics in its original form didn't respect that fundamental principle.
Yeah, that's a good way to put it. Schrödinger's equation, as it was initially formulated, it didn't inherently incorporate this cosmic speed limit, and that actually led to some potential violations of causality in certain theoretical scenarios.
Oh, really?
Yeah, it seemed to suggest that under some circumstances, influences could travel faster than light.
Which just can't happen.
Exactly. And if that were true, it would completely undermine our understanding of cause and effects.
Right.
You know, what causes what. It's a big deal.
Yeah, absolutely. So that incompatibility with relativity was one major hurdle.
Yes.
What was the other significant limitation of standard quantum mechanics that you encountered?
So the other really crucial limitation was that it couldn't adequately describe the creation and annihilation of particles.
Okay.
Standard quantum mechanics was great at describing how a particle's wave function evolves over time. So essentially how an existing particle behaves.
Right.
But it didn't have the tools to explain processes where the number of particles or even the types of particles could change.
Right.
Like, for example, in radioactive decay processes, like beta decay.
Okay. And just to remind everyone, beta decay is when a neutron in an atom's nucleus transforms into a proton.
Yes.
And in the process, it emits an electron and an antineutrino.
That's right.
So it's a fundamental change in the particle composition.
Yeah. And to be even more precise about beta decay, what's really happening at a deeper level is that a down quark within the neutron changes into an up quark.
Okay.
And that's what transforms the neutron into a proton. And this process also involves the emission of a W boson, which is a force-carrying particle.
Right.
And then that W boson rapidly decays into an electron and an antineutrino.
Okay.
So standard quantum mechanics, which was designed to work with a fixed number of particles.
Yeah.
It just couldn't account for these sorts of changes in the fundamental constituents of matter.
So to put it simply, quantum mechanics was great at describing the lives of existing particles, but it couldn't really explain their birth or their death.
Yeah, that's a nice way to think about it.
So that sounds like a pretty significant gap in our understanding.
It was a major problem.
Okay, so this brings us to quantum field theory.
Right.
How does QFT overcome these limitations and provide this more complete picture?
So QFT tackles this challenge by shifting our focus from particles to fields.
Okay.
It's a sophisticated mathematical framework that elegantly combines classical field theory. Think of things like electric and magnetic fields, those omnipresent entities described by Maxwell's equations, with the principles of special relativity and quantum mechanics.
Okay, so instead of viewing particles as the fundamental building blocks,
Yeah.
QFT posits that the underlying reality is actually made up of fields.
That's the central idea.
That's a big conceptual leap for a lot of people.
It is.
So these fields, they're not just empty space, are they?
No, they're not.
They're active even when there aren't any particles present.
That's right. Even in what we perceive as empty space, these fields are constantly fluctuating, teeming with what we call virtual particles.
Okay, virtual particles, we hear about these mysterious entities.
Yeah.
What are they exactly in this QFT picture?
You can think of them as fleeting quantum fluctuations within these fields. So within each field, antiparticle pairs can spontaneously pop into existence and then almost immediately annihilate each other,
Wow.
borrowing a tiny amount of energy from the vacuum for a very brief moment. And this is allowed by the uncertainty principle.
Okay.
So it's like nature gives them this temporary loan as long as they pay back the energy super quickly.
I like that analogy.
Yeah, these virtual particles aren't generally directly measurable, but their effects are definitely real.
Okay, so there's this underlying buzz or activity within the fields, even in their lowest energy state.
That's a good way to think about it.
So how do these virtual particles relate to the real measurable particles that we can actually detect?
That's where the analogy of a turbulent ocean can be really helpful.
Okay, I like analogies.
Imagine a quantum field as this vast ocean. Even in its calmest state, there's this background level of turbulence. And that's analogous to these virtual particles constantly popping in and out of existence. Now, if you add enough energy to a specific point in that ocean, you can create a large wave, a disturbance that propagates outwards. And that's definitely measurable.
Right.
In QFT, real measurable particles are like those large waves. They're quantized excitations in their respective quantum fields that arise when enough energy is concentrated at a particular point.
Quantized meaning that these excitations can only occur in discrete amounts.
Exactly, not just any random amount of energy.
Yeah.
They can only exist in integer multiples of a fundamental unit of energy for that field.
Okay.
So for example, you can have 1 unit of excitation in the up quark field, which we perceive as a single up quark, or 2 units, or 3 units, but not, say, 1.5.
Right.
Particles are like these quantized ripples or bundles of energy in the underlying fields.
Okay, so particles are fundamentally these discrete excitations of these continuous fields.
Precisely.
That's a really helpful way to visualize it.
Good.
So if particles are just these localized excitations in their respective fields, how do these fields explain the interactions between particles?
Okay.
The fundamental forces that we observe.
Right, so interactions between particles occur through the exchange of energy between these underlying quantum fields.
Okay.
And this exchange is mediated by another set of fields, the boson fields, which are the force carriers.
Okay.
So for instance, when 2 electrons repel each other electromagnetically, what's happening at the level of QFT is that the electron field of one electron interacts with the photon field. And this excitation in the photon field, the photon itself,
Right.
then interacts with the electron field of the other electron, transferring energy and momentum.
Okay.
And this results in the repulsive force that we observe.
So the photon is the force carrier for the electromagnetic force.
Exactly. And similarly, the strong force is mediated by gluons and the weak force by the W and Z bosons.
Okay, so forces aren't these mysterious actions at a distance, as Newton initially described gravity,
Right.
but rather they're the result of these interactions between quantum fields,
Yes.
these exchanges of energy carried by other particles, the force bosons.
That's a really key insight.
And this framework also elegantly explains things like beta decay,
It does.
which, as we said, pose a real challenge for standard quantum mechanics,
Yeah.
with the neutron transforming into a proton, emitting an electron and an antineutrino.
Right, a process where the number and types of particles change.
Exactly. So how does QFT handle this?
So in QFT, we start with the relevant quantum fields.
Yeah.
So we have the down quark field, the up quark field, the W boson field, the electron field, and the antineutrino field.
Yep.
Beta decay happens because the down quark field within the neutron interacts with the W boson field, causing an excitation in that W boson field. This interaction also changes the down quark field to an up quark field, transforming the down quark into an up quark.
Okay.
The W boson being unstable then almost immediately decays by transferring its energy to the electron field and the antineutrino field, creating the electron and the antineutrino as excitations in their respective fields.
So it's not a single particle just spontaneously breaking apart?
Right.
It's this dynamic interaction and energy transfer between these fundamental fields that results in this change in the number and types of excitations.
Exactly.
The particles that we observe.
And the underlying fields are always there.
Right.
What changes is the distribution of energy between them, leading to the creation and annihilation of those particle excitations.
That's really profound shift in perspective.
It is.
And crucially, while the number and type of particles can change,
Yes.
the total energy contained within all those interacting fields, it remains conserved.
That's right. It's just being redistributed among the different fields.
And another major triumph of QFT, as your readings highlight, is its compatibility with Einstein's theory of relativity.
Absolutely. That's one of its key strengths.
Yeah.
Quantum field theory is designed from the ground up to respect the principles of special relativity, and it resolves those troubling causality violations that plague non-relativistic quantum mechanics.
Right.
It gives us this consistent framework for understanding the universe at both the quantum level and at speeds approaching the speed of light.
Right.
That relativistic nature is a really important part of its power.
So it sounds incredibly powerful and elegant.
It is.
But as with any scientific theory, there are still open questions.
Of course.
And areas where our understanding is incomplete.
Yeah, for sure.
And you mentioned that even QFT isn't a perfect final theory.
Right.
So where does it fall short?
One of the most significant gaps, and this is a big one, is the absence of a complete and universally accepted quantum field theory for gravity.
Okay.
We have the standard model, which is a specific formulation of QFT. It describes the electromagnetic weak and strong nuclear forces incredibly accurately.
Right.
But gravity has so far resisted this kind of quantum field treatment.
So we haven't figured out how to fit gravity into this framework.
Not yet. We haven't been able to develop a fully consistent and testable theory for the graviton.
Right, the hypothetical particle that would mediate the force of gravity in QFT.
Exactly. It's like we have this amazing toolkit for almost all the fundamental forces and particles.
Yeah.
But one crucial tool, the one for gravity, is missing.
That's a pretty big puzzle.
It reminds me of that saying, if all you have is a hammer, everything looks like a nail. Our current best hammer is QFT, and it's been remarkably successful in explaining so much.
Yeah.
But the fact that gravity doesn't neatly fit in, maybe it suggests that gravity is a different kind of nail altogether.
Okay.
And needs a different tool. Or maybe we just haven't figured out how to use our QFT hammer effectively for this problem yet.
Interesting. So despite these open questions, you called QFT probably the most beautiful theory in science.
I did.
Why does it hold this esteemed position in the eyes of so many physicists?
I think it's because of its profound implications about the interconnectedness of everything in the universe.
Okay.
QFT reveals that what we perceive as these separate, distinct entities, us all living things, the planet, stars, galaxies, even our thoughts and dreams, they're all ultimately just different kinds of excitations in the same underlying quantum fields.
Wow.
These fields extend across all of space and time.
So when we encounter those more philosophical or spiritual ideas about a fundamental unity to the universe, QFT actually provides a concrete physical basis for that concept.
I think so. The universe isn't just a random collection of separate things. It's different manifestations of the same fundamental stuff, these ubiquitous quantum fields.
So we're all essentially ripples in this vast cosmic ocean of energy.
That's a beautiful way to put it.
And another remarkable thing is that we as humans have developed the capacity to understand this.
I know. It's amazing, isn't it?
At least to a certain degree.
Yeah.
We can probe these most fundamental layers of reality and build these incredibly sophisticated theoretical frameworks like QFT.
It is pretty mind-blowing.
It really is. Okay, so to summarize our deep dive today, we've traced this evolution of understanding, starting from those more ancient, less structured views, moving through the deterministic clockwork of classical mechanics, then to the probabilistic and somewhat limited world of quantum mechanics, and finally to this more complete relativistic and field-based picture of quantum field theory.
Right.
And the key shift here is moving away from thinking about particles as the primary reality and recognizing that these underlying quantum fields are the fundamental entities, with particles being just those localized excitations within those fields.
That's the big takeaway.
And QFT gives us the framework to explain not just how particles behave, but also how they can be created and annihilated, and how those forces arise through the exchange of energy between these fields.
That's it ties it all together.
It does. It's a unified framework that resolves so many of those inconsistencies and limitations of earlier theories.
It does.
And it offers a much deeper and more coherent understanding of the universe.
It's a beautiful theory.
It really is.
Yeah.
So So as we wrap things up today, let's leave everyone with a final thought to ponder. Considering that everything at its most fundamental level can be described as excitations in these quantum fields, what are the broader implications for our understanding of reality itself?
Hmm, that's a great question.
What about phenomena like consciousness
Yeah.
or the very nature of existence itself? And knowing that even QFT has limitations, especially that missing piece of a quantum theory of gravity, what other profound insights about the universe might still be out there waiting to be discovered?
There's still so much we don't know.
It's a lot to think about, but hopefully this has given you a foundation to explore these concepts further.
Yeah, I think so.
Thanks for joining us for this deep dive into quantum field theory.
Thanks, everyone.